Hello, this is Lab Lesson 4A on Assembly Modeling in Inventor. We actually got our first look at assemblies in Inventor in the last lab lesson where we designed gears using the Design Accelerator. And in this lesson, we will apply what we learned about assemblies from Lecture 4A to combine solid models into complex systems. Doing so involves applying constraints to remove the solid model's degrees of freedom and to obtain the desired arrangement and interaction of parts within our assembly. So we will talk about this in addition to some inspection tools that can prove useful in making assemblies. We'll consider this door hinge example as an example throughout this video, and this video will be followed up by another short example of the second assembly shown on this slide. Starting with a quick review of Lecture 4A, recall that solid modeling isn't used on its own to create a finished product. Many devices have multiple components to them, and assembly modeling allows us to combine those components together in a computer model to create a device or structure called an assembly. This is actually reflected in Inventor's symbols for part and assembly files, where the part files are represented by these yellow cubes, and the assembly symbol is a combination of these cubes, since assemblies are composed of solid model parts that we call components. Assemblies can also be combined into larger assemblies, and in this case we call the smaller assemblies that come together sub-assemblies. For example, consider a bicycle assembly, which could be created from a set of sub-assemblies. One of these could be a wheel sub-assembly consisting of wheel spokes, a hub, a rim, a tire, and a valve component. Another sub-assembly might be for the front set, consisting of the handlebar, the front brakes, and grips. And each of these sub-assemblies are assemblies in their own right, since they are constructed from a number of components for the purpose of performing a specific function, but they come together with other sub-assemblies to make the larger bicycle assembly overall. So with this review out of the way, let's get into the steps of making an assembly in Inventor. As we've seen before, the first step is opening up an assembly file, and we can open a template in units of either inches or millimeters depending on what suits us. Once we have a new assembly file open, our next step will be to place our components into the assembly file, and then apply constraints to fully define the relationships between components. Those are the essential steps to making an assembly. Finally, it is important to know that the assembly file is linked or associated with the part file of all of its components. So if you want to share an assembly model with someone else, you can't just share the assembly file. You have to share the part files as well. For this reason, the last step we are going to learn is how to save your assembly using Pack and Go, which will zip all of the necessary files together for sharing. So once we open a new assembly file, the assembly interface is slightly different from what we saw for part modeling. To start, you'll notice that the toolbar looks a little different. We don't see our modeling tools anymore. Now we have an Assemble tab in addition to the Design tab that we saw in our gear design lesson. Our project browser also looks a little different. With solid modeling, this browser listed all of the features of our part, but we will see with assembly modeling that this browser will list which components we have placed in our assembly instead, as well as the constraints that we apply to them. So our next step is to place components, which we can do by clicking the Place button in the top left of the Assemble toolbar to bring up a pop-up menu. It is possible to model parts inside of an assembly file, but it is good practice to have everything modeled before beginning your assembly. Then placing components is much like placing views in a drawing, where we can navigate to the part file we want to place in our drawing, and then click anywhere in the viewing area to place that component. If you want to change the orientation of the part before you place it, you can right-click to rotate it. You can also place multiple instances of the same component in an assembly file by just clicking again, and once you've finished, you can either hit Escape, or you can right-click and finish placing. Once our components are placed, the next step is to apply assembly constraints to bring the degrees of freedom of each component down to 0. Recall that each component has 6 degrees of freedom, 3 in translation and 3 in rotation, which we can see by going to the View tab and clicking Degrees of Freedom. After initially placing components, each will have 6 green arrows to indicate their 6 degrees of freedom, and we are free to move these components around. But in an assembly, we want the components to be set up in such a way that they are all constrained to the correct spot or to movement in a particular behavior. As we apply constraints to establish the relationships between the position and orientation of parts, these green arrows will disappear. With the first base component that we place, however, there are no other components to constrain it to. So rather than applying constraints to the base component, we ground it instead. We do so by right-clicking on the component and selecting Ground. This eliminates all degrees of freedom of this component so that it can become the fixed point of our assembly that all other components can be constrained to. We can confirm that this part is grounded by hovering over it and seeing a little pin and the electrical ground icon pop up by the mouse. The same pin icon is seen on the part icon in our assembly browser to the left, which also tells us that this part is grounded. Make sure that you only ground one base component and that you apply constraints to the rest, as grounding multiple components will just lead to issues with your assembly model down the road. So let's ground this base component of our door hinge and then discuss assembly constraints that we can apply to the rest of the components that we place in our assembly using the constraint tool from our assembly toolbar. We will focus on 4 main assembly constraint tools in Inventor, which we've already introduced in lecture 4A. The first assembly constraint is called a mate-mate constraint, which takes 2 parts and it aligns them together. There are 2 common uses of this tool. The first one is face-to-face, where we select a single face on 2 parts and they will be stuck together with their normals facing opposite directions. This can also be used to align the center axes of cylindrical features with each other. The second use is the flush constraint, which aligns 2 faces to be within the same parallel plane and facing the same direction. We use this term flush to describe when 2 faces are in line with each other, almost seeming like a continuous face. In both cases, to apply these constraints, you just have to select the constraint tool, select the appropriate constraint type in the pop-up window, and then select the 2 faces in your assemblies that you want the constraint applied to. Then you can click Apply, and your assembly model will be updated to include the constraint. Also note that it is possible to apply an offset to this constraint so that the faces are not in the same parallel plane, but instead are offset by the distance indicated. The process of using the angle constraint is much the same, but in this case we specify a desired angle between 2 faces, edges, or axes. This is a very useful tool when 2 things aren't flushed or mated with each other, and they have a certain angular gap between them instead. We also have a tangent constraint, which is mainly used for curved objects to ensure that they contact tangentially to other curved or planar surfaces. There are 2 modes of the tangent constraint: an inside mode that can be used, for example, if we want to insert a rounded rod into a rounded divot. The second mode is the outside mode to make a curved surface contact another curved or planar surface from the outside, as seen here. This is a fairly uncommon constraint, but it is good to know how to use it nonetheless. Lastly, we are going to look at the insert constraint, which combines a face-face and an axis-axis mate constraint into one single constraint, and it is really handy for inserting components like bolts and screws into other components. So let's return to our door hinge example and apply some of these assembly constraints to fully define the relationships between components. There are a number of strategies that we could take to fully constrain this assembly, and one of these strategies that I'll now walk through is listed on this slide. Here I have all 3 of our components in the assembly file, with the bottom hinge grounded already and the top hinge plate and the pin entirely free to move around. Our first step might be to use a mate-mate constraint to constrain the center axis of the hinge pinholes together. This prevents motion in 2 of the dimensions, but the top hinge plate can still slide along the axis and rotate in one direction, which we can verify by the green arrows if we show degrees of freedom in our model. These constraints also get documented in the assembly browser under the components that they were applied to. So if we ever need to remove a constraint or edit it, we can right-click on the constraint in the assembly browser to either delete it or edit it. We can then use a mate-mate constraint to align the hinge plates to each other, as seen here. Alternatively, I could have used the flush option to make these 2 right side faces flush, and that would serve the same purpose. This just goes to show that there are many ways to accomplish the same task. Some things just depend on your personal preference and exposure to the available tools. Either way, this constraint restricts the remaining translation movement of the hinges, but we still have the rotation degree of freedom remaining. To remove this rotation degree of freedom, we can apply an angle constraint. There are a few options when it comes to the angle constraint. Our first option is the directed angle constraint, where we can select two planes, and then we can specify the angle we want between the two normals of those planes. In this case, if I select the two faces of hinge 1 and hinge 2, I'd have to specify an angle of 180 degrees between these two normal arrows for the door hinge to be closed. An angle of 0 degrees would be open. Another option is to use the explicit reference vector, where we have to make a third selection that will represent the z-axis or cross product of our first two selections. In the directed angle constraint, this z-axis vector is inferred, which means that the direction of our angle might have to be flipped, like negative 180 degrees instead of 180 degrees, whereas with the explicit reference vector, it is explicitly selected, as the name indicates. In most cases, the best choice of this third z-axis vector product selection is the axis about which our first two selections are allowed to rotate. As we saw, we can manually set the angle between the two brackets, so we can control if we want the hinge to be fully open, fully shut, or somewhere in between. This is practical because we might want our assembly model to show the extent to which our door hinge assembly can open or close. After making this angle constraint, 0 degrees of freedom remain with the hinges, but our hinge pin still needs to be constrained. We can use the insert constraint to remove many of these degrees of freedom by selecting the base of the pin cap that we want mated to the hinge plate, and then selecting the top of the hole on the hinge where we want the pin inserted. When we apply this constraint and view the degrees of freedom, we see that our pin is still able to rotate, and there are a few ways that we can constrain this. We could use the angle constraint to set the angle of one of the pin's origin planes to be aligned with one of the planes on our hinge plate, or we could go back to our insert constraint by navigating to it in the assembly browser, right-clicking to edit the constraint, and then checking off this box to lock the pin's rotation. This removes the last degree of freedom, so we are done with this example. We can also use this Show Constraints button to see the symbols representing all of the constraints that we've applied to this assembly. Our final step for this demo will be to save our assembly file and all of its dependencies in a zipped folder. Remember that this is a very important step if you want to share an assembly model with someone else. You can't just share the assembly file because it is linked to the part files of the components in it. So if you just shared the assembly file, the person you sent it to wouldn't be able to open it because Inventor would not be able to find the part files that the assembly is dependent on. So we need to collect all of these files together for sharing, and Inventor has a tool specifically for this called Pack and Go that zips all of the necessary files together into a zip file for sharing. To use Pack and Go, go to File, Save As, Pack and Go, and a Pack and Go window will pop up. Here we can select the destination folder where we want our file zipped to. So you can click on the magnifying glass and create a new destination folder titled appropriately. I will call this one Lab 4 Example 1. Then we want to look at the checkbox options to the left here. We want to make sure that we have skip libraries, skip styles, skip templates, and package as zip checked off, and collect workgroups unchecked. Then we can press this Search Now button for Inventor to look for all of the necessary files, which should show up in the Files Found box below. Then we can click Start and Done. And if we check the File Explorer, we should find our zip folder that is now ready for sharing. If you extract it, you'll find that it contains the assembly file in addition to the part files and details required to retain links to reference files. So this covers the main steps of assembly modeling, from opening a new file to saving it using Pack and Go. There are also a few useful tools that you might want to use while modeling assemblies, and the first that we'll look at is the Measure tool, which you can also use in part modeling. You can find this tool under the Inspect tab here, or you can use the hotkey M to bring it up. This tool can be used to measure a wide variety of things, such as linear distance, length, angle, area, and so on. Just like with any other tool in Inventor, you can exit out of it by pressing Escape or by right-clicking and pressing Done. The second tool we'll introduce is the Analyze Interference tool, which can be used to tell us when there is an issue with our assembly. We can either highlight all of the components or select two specific sets of components, and Inventor will check for interference between those components. If there are any collisions or interference between components, this tool will highlight those regions and make it easier for us to identify that there is overlap, as seen with the red highlighted interference of the rod and mounting bracket to the left. If you do find that there is interference between components, then this might be an indication that one of your parts is either not modeled properly or not constrained properly. In other cases, like with this bolt and nut, we can see interference of the threads, but this is acceptable for our purposes in this course, as is interference of gear teeth if the gears are just not lined up properly in the assembly model. In this case, you just have to use your engineering judgment that as long as the thread size or gear tooth module is modeled correctly, then we can ignore this interference, because it's just showing that these components aren't exactly aligned properly. So these two tools might come in handy as you work through other assembly modeling examples and assignments. Here's a second assembly example that will be modeled in an accompanying video, and two additional examples are posted with the course material for your individual practice. As with our previous lab videos, we'll end off with a few tips related to assembly modeling. Two tips are to always turn on degrees of freedom to see what is remaining to be constrained, and the second is to use the Analyze Interference tool to make sure all components are properly constrained as you make your assembly. A final troubleshooting tip is just to make sure you are aware of what happens if you remove or rename a part or subassembly file that an assembly file depends on. If you move or rename a part file that your assembly file is linked to, this will cause issues when you try to reopen your assembly file, which you can correct by redefining the path to the part files when you reopen your assembly. So just be aware that moving or renaming files might cause this issue. For example, here I've changed a part's name from mount to mounting bracket, so when I open up an assembly that contains this part, I have to resolve the link to this part file by selecting the newly named mounting bracket to open, so just watch out for that if you rename or move anything. This wraps up this lesson on assembly modeling in Inventor. In the next lab lesson, we will learn how to make assembly drawings in Inventor, including this exploded view drawing of our door hinge.